All right, so here we're going to be doing vectors in 2 dimensions. Um, we'll touch. They're going to be some in 3 dimensions. Um, we might do 3 dimensions here and there. Do I have to copy the questions for the notes then? Um, if you're doing it by hand, just kind of just kind of mimic the notes. Write this down as I go through it, and then write this down. Um, I mean, you can abbreviate stuff, right? You can just say a vector and just write this. That makes sense. Vectors in a coordinate plane where this is, let's say this is, and just put like an arrow, this is horizontal, this is vertical, something like that. Okay. All right. So we're going to do vectors in 2 dimensions. You're going to notice the difficulty level of this class went from like the hardest section, which is like 7.5 and like 17.3. Those are really hard sections. We're going to go back to vectors in 2 dimensions, which just takes the difficulty and just dumps it again. So let's go through this. So have you guys messed with vectors before? I'm guessing yes, but I don't know. I'm going to teach it as if you haven't. Not that I remember. Yeah, I'm going to teach it as if you haven't, but we're going to just go through this slowly. I don't remember. Okay, so let's just go through it. All right, so a vector represents an ordered pair of real numbers. And so here we're going to have a vector v. We write it with a v with a little arrow on it, right? Well, at least that's how we mathematicians symbolize it. Maybe not so drastic, but they just do this. They actually don't do the full arrow. They just put a little hat on it, I guess. And then here we're going to have a is going to be your horizontal component or your x component, and your b is going to be your y component. And you have it in kind of brackets or braces. Um, so here we can break it up into things. So sketch a few representations. So notice that a vector has a magnitude. I guess I should write this down. A vector has a magnitude. I'm going to take these notes and use them to update them and make them better. A magnitude and a direction. But it doesn't have any position in space. So here for the vector 2, 3, I can go over 1, 2, and go up 1, 2, 3. And this is a representation of this vector, right? We call this the tail, and this the head. And so you just draw it as an arrow. And so the tail is where it starts, and the arrow is where it goes. And so this is one representation of the vector. Another representation of the vector is if I start here at the tail, I go over 2 and up 1, 2, 3. And so notice this has a magnitude. We'll get into how to calculate that magnitude in a second, but this has some length right here and a direction. It goes in that direction. It goes in, this theta, right? So we'll define this later, but I guess let's go ahead and do it here. We'll have some magnitude v. We'll call it some magnitude and some direction theta. And so let's do another one here for if I have -1 and then 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I can count today. Here's a representation of it. Another representation would be here. I'll go down to here actually. And then 1, 2, 3, 4. So this is another representation of it. This is another representation. So it's always in the same length and same angle, right? Same direction. So here, I'm going to draw another one over here for this one. 2 and 3. 2 and 3. And so a vector is not locked at any place, though the standard way to draw it is at the origin. That B seems strangely familiar. Were there vectors in physics by any chance? Yeah, there's vectors all over physics. In fact, physics is nothing but vector calculus once you get to it. Are you just planting them in random places? Yeah, so I'm just planting them in random places because I want to emphasize that a vector doesn't own a position in space. It's nothing more than a direction and a magnitude. So this is the same. This is a representative of it. This represents it. This represents it. This represents it. This represents it. It doesn't matter where I draw it. It matters that this has a length of -1. And, go -1 in the horizontal direction, 5 up, 5 in the vertical direction. So a vector, I'm just trying to hit home that the vector does not have a spot on a coordinate plane. So that's why I'm doing that. All right, the components of a vector. So if a vector is represented in a plane with an initial point, P, and a terminal point, Q, so here we can also say instead of head and tail, initial and terminal point, you can calculate the vector just by taking the difference in x's and difference in y's, something we've done. We've done 1,000 things like this. And so here, if I was going to just use this one as an example real quick, here we have 2, 3 is my terminal point, right? Here's my terminal point. So Q would be 2, 3. My initial point is 0, 0. And so my vector here is 2 minus 0 and 3 minus 0. So I get the vector 2, 3. Another one we could do is, let's take this one, right? So my initial point is, so here, let's just do this one again. Let's just do Q. So my initial point here is this one. So positive 2. And then -6. And then my, oops, that's not, my terminal point is 1, 2, 3. Hold on, I wrote this on the wrong one. And I'm not on the right layer. All right, let's just. My initial point, my initial point here is 4 minus 3. And then no, I can't just seem to write today. All right, let's try this again. Here's my P, this is my Q. P is 2 minus 1, 2, 3, 4, 5, 6. So 2 minus 6. My Q here is 1, 2, 3, 4 minus 3. And then here we can just run through the same thing again. Here we'll have 4 minus 2, -3 minus a -6 will be plus a 6, will give us 2, 3 again. Okay, so here, given any 2 points, you can do that. Vectors can also, another way of writing vectors instead of in its kind of braced form is in component form, where you have A equals I plus BJ, or AI plus BJ, where this is just writing where I is the unit vector. I guess I needed to write that down. I is a unit vector. And it's a unit vector 0, 1, and then J, and the little hat. That's how you write it if you didn't use the bold, is the unit vector. Even Christmas. It's 1, 0. I is in the x direction. J is in the is the unit vector in the y direction, which is 0, 1. Sorry about that. My dyslexia is really bad today. It's okay. We'll get by it. I'll be extra careful from now on. Now that I've realized it. So here we can see these are two unit vectors. Have you guys seen this IJ notation ever before? Yes. Yeah. Okay. So for some people this is familiar. Some people it's not. Maybe. Basically, I is the unit vector in the I is the unit vector in the x direction, so it has a length of 1 and it points along the x-axis, right? J points as a length of 1, and so here it goes along the y-axis, And then you'll have k in the z-axis if you have k and goes from there. And usually you use ijk if you only have 3 dimensions. If you go to higher dimensions, you don't usually use it. So if you're going to write these in terms of I and j, all you have to do is just say this is equal to 2i, and put a little hat, since we don't have a bold font, we put little hats on it, minus 3j. This will be 0i, so this is just 4j with a little hat on it. And then this is 3/5 I minus 4/5 j. It's just another way of writing vectors. And so these are equivalent. I'll leave that up for a second before swapping pages. All right, let's go ahead and move to the next page. All right, next page, please. Thank you. All right, so let's talk about a magnitude of a vector. So we want to figure out what that length is, right? So here we have a bunch of vectors, or the magnitude of the length, right? So if we want to figure out what the length of our vector is, we use this formula right here. And so we denote it as, a solid, so it kind of looks like the absolute value. Technically it's not, but that's what we denote, right? Of a vector is its length. And here, if I was going to figure out the length here, if I'm 2 in the x direction and minus 3 in the y direction, right? Here I have 2 minus 3. How would I figure out the length of this? Well, it's just Pythagorean theorem, right? And so this would be my c, so c equals the square root of a squared plus b squared, right? See why this comes right after the triangles. And so here the length of this would be 2 squared plus minus 3 squared square root. So this is 4 and 9. So this equals to the square root of 13. Doesn't simplify anything better than that. The length of this vector is 0 squared plus 4 squared, which of course is just 16, which is of course just 4, which makes sense. All my distance is in one direction. I have no distance the other, so it is just that distance. For c here, I'll have 3/5 squared plus a negative 4/5 squared. So let's crunch through this slowly. So I'll have 9/25 plus 16/25. I'm going to take the square root of that. The square root of this will be 9 plus 16 is 25. So 25/25, which of course is just the square root of 1, which is just 1. So this has a magnitude of 1. So the length of this vector, if I drew it, would be 1. The length of this one is 4. The length of this one is square root of 13. Or you could roughly put in whatever the value is. So these are the magnitude. This is how you find length of a vector. You're going to do a lot of this in engineering. You're going to have a force, right? You're going to have like someone's going to be pulling like a little wagon or something, right? And you're going to say this is 60 degrees and he's pulling it up this way, and you're going to want to figure out what the magnitude, how much force is there based off of how far it travels, and a lot of stuff like that. We'll get into it. We won't drag around the little wagon yet. All right, so here's some properties of vectors. If you add up two vectors or minus 2 vectors, that should be a v. Sorry guys, that should be a v. I'll put that in my notes for corrections. Yep, it's v everywhere else, just there. So u plus v is you just add up the components. So the a components add up together, or the first components add up together. The second components add or minus together, depending on what you did. If these vectors were in larger lengths, you just keep adding the components. So if this had like C1 and C2, you'd add up C1 and C2 and on infinitum. If I multiply some scalar, so this is a vector, which means it has components to it. So it has an x, y, and z. A scalar just means a number. It's just another way of saying a number, like the normal numbers you deal with. So if I have a scalar or just a number, so if I take 3 times the vector, 3 times the vector u, it'll just be 3 times the um, 3 times the horizontal component plus 3 times the vertical component. If I adding 2 vectors, you can swap the order. This isn't guaranteed in later math. You might say, well, that's obvious. You can always just swap. And, this is, you can group them any way you want. Say if I'm adding up 3 vectors, I can, this is called the commutative property. And this just means I can commute them. This is the associative property. This is the additive identity property. These all have very, very specific, this is the inverse property. These all have very specific properties we talk about. Don't worry about any of the names, right? Do not worry about any of these names at all. Just notice that you can flip these, do this. Basically what this little property of vectors chart allows you to do, what it allows you to do is just to operate as you normally would think to operate. Here, if I have this, I need to get rid of that. That needs to get rid of. Here, if I have c times this, I can distribute it in. This is your distributive property. 1, this is the multiplicative identity, and this is the 0 property. And here I have 0 vector. Notice 0 and 0 vector do not equal each other. This is a scalar, this is a vector. And the 0 vector usually means 0, 0. It has no direction and no length. So that is slightly different. Okay, you really don't need to make any notes on this except fix that to make it a B. All right, so let's get to our last section. All right, so here we're going to do this basic arithmetic. I'm going to teach you how to find the magnitude and direction of a vector, and then we're going to do a word problem. I'm not doing any word problems for these sections for the final. I'm not saying that no word problems. That's not what I'm saying. I'm just saying you probably won't have word problems for vectors for the final. I can almost guarantee I won't do that to you. All right, so let's do this. So here, if I have 2 vectors, find the following. So if I want to add up 2 vectors, so here, u plus v is going to equal to, here you just take each of the components, 2 plus a -1, comma, -3 plus 2. And so if I do that, I'm going to get 1 minus 1. Here, if I want to take 2u, we're going to just do that. We can just put, so it'll be 2 times 2, and then 2 times -3, right on the right layer. So here I'll get 4 minus 6, which is 2 times this vector. And then here we can solve, do simple expression. So do I know what 2 times u is? Yeah, I already did that. It's 4 minus 6. Minus was 3 times v. Let's go ahead and crunch that through. That'll be -3, positive 6. And then here we'll just do the subtraction. So I'll have 4 minus a -3. And then I'll have -6 minus a -6. Oops, no, minus a positive 6. So what do I get here? I'll get 4 minus is plus, so 4 plus 3 is 7. And then here, I'll have 6 minus 6, which is -12. Okay, so each one of the homework just literally, I'm having you just do different numbers for these. All right. All right. So what do we have here? So here, so the horizontal vertical component. So given a vector, it has a magnitude and a direction. Not how you spell direction. Oh boy. So I need to swap that. Note to self, double check notes after you do it the day after. Then AB, so here we can split it up. So the A component is the magnitude of it times the cosine of the angle, and the B is the magnitude of it times sine of the angle. And so we can use this, if I know the magnitude and direction, I can therefore create the vector by just plugging it in. Or if I'm given a vector, I can reverse engineer what was the direction. So let's see if we can do that. So let's see if we can do this. So here I have the vector. Let's go ahead and write it in the form a little bit more. Let's write it in both forms. That way you can see it both ways. So what's the magnitude of this? What's the magnitude of so the first thing, if I want to find the magnitude and direction, I'm going to start with the magnitude. So here I'm going to have 1 squared minus the square root of 3. So here, first component squared, second component squared. So this gives me 3 plus 1. So this is the square root of 4. So this is 2. Okay. So here, we're going to have A equals 2 times the cosine of theta. And then we're going to have B equal 2 times the sine of theta. Do we know what A and B is? Yeah. A is minus square root 3. B is 1. So can we solve for theta now? Yeah, because we want theta to be, so cosine theta equals minus square root 3 over 2. Sine of theta equals a half. So what is theta? I'll let you guys try to crunch out what that number should be. So what is theta then? Let's see if anyone remembers their trig. What angle is, so first of all, what quadrant are we in? Let's just establish what quadrant are we in. I have sine of something is positive and cosine of something is negative. So what quadrant is that? Second quadrant, okay? Then I want to find the angle in the second quadrant, which will give me a half, and then negative 3 over square root of 2. And so sine of a half, well, sine of a half in quadrant 1, well, that was pi over 6, right? And so, and then that'd be the same here for positive, if we had this to be positive for a second. Positive cosine of 3 over 2, well, that's pi over 6, and then so cosine of pi over 6 is square root of 3 over 2. Sine of pi over 6 is a half, if you memorize the little things. So what's the reference angle of pi over 6 in this? Remember, it's the same angle here. So this is pi over 6. That means I'll have pi minus pi over 6, which gives me pi over 6. Yeah, someone got it. Somebody got it. So this is 5 pi over 6. Okay, so now I know what the magnitude of this. The magnitude here is, so the magnitude of V is equal to this, and then the direction is 5 pi over 6. And so that's how you can do that. We'll give you more of this. So you'll get a chance to play with this tonight, so I'll let you guys go and do that. So, all right. Let's do at least one word problem so you can at least have, this is something I want you to see. I didn't give you a word problem on the homework. So let's do this. A woman launches a boat from one shore of a straight river, right? So we're going to pretend we have a straight river. Not very realistic, but let's go for it, right? I wants to land a point directly on the opposite side. The speed of the boat relative to the water is 10 miles per hour, and the river is flowing this way at a rate of 5 miles per hour. In what direction she head the in what direction should she head the boat in order to arrive at the desired landing point? So she wants to travel straight this way and land at some point on the opposite side. So obviously she's going to, if this is at 5 miles per hour, right? Obviously she's going to want to go this way, right? Or at least head her boat this way. That way, as she rows this way, the stream pushes her, stream pushes, stream pushes, stream pushes, and then eventually it just ends up equaling out. Does that make sense why we want to do what we're doing? All right, so let's figure this out. So we know the magnitude. So here we want, so we can say I can say this correctly. See how I want to say this in a way that I don't confuse you. So this is, so we're going to have the boat right here. So the boat's traveling this way. The water's traveling this way. We want, if when we add up these two vectors, that we're going this way. Does that make sense? So we want, we want the addition of these two vectors to go this way. We know the magnitude of the water. So for the water, let's just say the water vector has a magnitude of 5 and a direction of, and a theta w of 0, right? It's heading straight in the positive x direction. We'll say the boat vector, we know what the magnitude is. The boat vector has a magnitude of 10, right? Because it's 10 miles per hour, right? So just simplify to 10. This is what we want to find. And what the question is, what direction? So this is our question. This is our goal, right? Write down the goal. It's always good to write down the goal. That's our goal. How are we going to achieve this goal? Well, we're going to have to add up the water plus the boat is equal to, let's just say true direction and true magnitude, right? Let's just do that. And we want it such that we don't care what the magnitude is, but we want theta of the true magnitude to be pi over 2, right? Because pi over 2 would be straight across. So straight north. Okay. So let's go ahead and figure this out. All right, so here, this is what I want. All right. How many, are you guys up with me what the goal is? How to do this? I wanted to do at least one rough problem. I'm not expecting you to do this. But you guys up with how the magnitude, directions, and the goal? This is kind of like what you would be doing in engineering. So I figured we should at least try. You guys okay with this? Sort of. Okay. Yeah. All right. At least you're going along for a gag. All right. So let's do this. So let's see how the best way to do this. So we're gonna have. All right. So here we're gonna have. So let's go ahead and add up these two vectors. Let's go ahead and add up these two vectors. So here, w plus b is equal to, well, w has, so here I'm going to have 5 because it's all, because another way of writing w would be 5, 0, because it's all in this direction, right? It's all 5, oops, plus 10 times the cosine of the angle I'm looking for, right? Because remember here, this is 10 times the cosine of the angle I'm looking for, right? comma, plus b, or so I know what the magnitude is, I don't know what the value is, but it's just, I'll just leave it as that. That's what I'm looking for. Then this is going to be 0 plus 10 times the sine of the angle I'm looking for. Okay. All right. All right, so here we can just grab this in isolation. So let's grab this in isolation real quick. And so we know that this one, since we want no horizontal component, we know that this wants to be 0. So we'll have 10 plus 10 cosine of theta is equal to 0, right? Because we want our direction to be pi over 2. So we want this to be 0, this to be whatever, right? And that, whatever that is, will give me this direction. Or another way of thinking about it is I want no horizontal component. I just want to go straight north across the river. So I want this to be 0. It's an equally valid way of thinking about it. So here, if we do this, we get cosine of theta. We minus the 5 across, so this will be minus 5/10, or negative a half. Well, negative a half is 2 pi over 3, right? So I'm going to be traveling. So here, this will be 2 pi over 3. And if I travel that, this component will be 0, because I just want to go straight across. All right, it's not like 100, like not 100, but not 0. Oh, so this one we don't care. All we want to know is where we want to head the boat. Can we figure this out? Yeah, now I know this is 2 pi over 3. It's 10 times 2 pi over 3, which is square root 3 over 2. So it'll be 5 times the square root of 3 would be the other component. But that's not necessary for solving our equation. We just want to know in which direction do I head that I arrive exactly. I'm going to do 2 pi over square root 3. That's the angle, right? Or we could write it, another way of saying this is 120 degrees. And in fact, since we learned how to do it, we're going to go north. And then we're going to turn 30 degrees west, because north would be 90. So north, 30 degrees west, if you want to do like the old directions we learned. You don't need to know this, but just in case you're doing that.